Hello, hello.
Hello.
Okay. Um, okay. I There's one technical feature that I haven't figured out, which is how to admit people without clicking on them. So sorry about this. I think that I will have to, until I figure it out, I will have to keep on checking the list and clicking throughout the lecture. Uh, Sorry about this. All right. So let me switch the chat on. Um, okay. All right. Okay. Yes, somebody posted some sort of wolf picture. Now I don't understand. Does everybody sees a wolf instead of me? Okay. Okay. I guess so. Here is the thing. Okay, great. Thank you. So because we have 100 people in the class, of course it's hard to arrange it like as a true interactive thing. But so I'm muting you by default. On the other hand, so there's two ways you can say something. One is write it at a chat, except that I would ask you to abstain from, writing some funny stuff, because I'm trying to scan this and check for like real questions and points. And some of what you say is very helpful, but sometimes some people write something that, it would be better if they just abstain from that. And if you really want to say something, then you can unmute yourself, I think, and say it. Okay, so that being said, let's go to the presentation. Right. So okay, so now I shared the screen with you, and it's my slides. I also uploaded them to the class website. So I made some changes, some edits. So if you upload the most recent versions, then you get the ones that I'm going to speak about today. All right. Okay, so there is also like a little slide presentation that I should have said in the first class about what discrete mathematics is good for in general. Why are we studying this? Please do see these slides, they're kind of cute. But we have a lot of logic to cover, so let's just jump into that. One more administrative thing is that, well, of course, whoever downloaded the homework might have noticed that there's quite a lot of, there's these logical exercises, and I'm trying to drum stuff so that people do stuff from different types of questions. In the end, there's quite a lot. So you might want to start early, especially if you are relatively new to this stuff. Okay, and use the Piazza to point out whatever it is, that you want to point out about this. Okay, one more administrative stuff, sorry about that, is that some people among faculty, they talk like that maybe it's more useful if instead of this kind of long lecture, I structured this so that, like, for example, I just have like a 45 minutes and then have just a separate video, like 45 minutes later on, and just post that. Well, we'll see how that goes. That could be a better format. So we have just some part with questions and answers and some part without, but you get less tired if you see it in a shorter fragments. Okay, let's see. and I can take your feedback on that and see what fits better. All right, so let's go. Logic is basically the first chapter. There's quite a bit of material. Okay, what's going on? All right, good. Admit, oh, sorry. There's this waiting room. Okay. This, I think, is going to make for pretty terrible recordings, because if you watch it offline, because I'm constantly checking the chat and I'm admitting people that are showing up in this box. All right. Okay. Hopefully, I'll get better at this the further we go. Right. So, what is logic? So, it's a branch of mathematics where everything we talk about, every variable has only two values, truth and false. Okay, unlike, say, arithmetics, where you can have integer arithmetics where the values are integers, or general arithmetics when the values are real, or complex analysis where there are complex numbers, etc. Right? But here, like, we have the simplest setting, really. There's only two possible values. You cannot really have any arithmetics if there's only one possible value, right? Like, that will be kind of an uninteresting system. And interestingly, the system, when you can have just two possible values, you already can do a lot, and it can get very complicated. So that's kind of weird. So logic is relevant to CS incredibly, right? So if you just think of digital logic design, so Boolean circuits, all the hardware. So basically, what is it? A bunch of gates, right? Like wired. And what are the Boolean? The Boolean gates are Boolean operations. There are ANDs, ORs, XORs. And all of it is a one-to-one relation with logical operations. So somehow from hardware that does logical operations, we get computers. So somehow from logical operation formulas, we are able to create computing that basically does everything, seems like, right? Like, it can emulate a human brain for all we know. Not yet, but perhaps soon. Yes, so, okay, that's the power of logic right there. Obviously, artificial intelligence, automated reasoning, constraint propagation, these are all basically Boolean circuits. Proofs that algorithm is correct, that it has some liveness properties, robustness properties. In my field of cryptography, that it is secure is the most important proof you want to make, right? And if you if you don't understand logic, there's no way you can understand or parse a proof. And there's many more uses. So basically, it's useful in any area where you want to have precise statements and you want to reason about things in a systematic way. So, okay. Logic deals with propositions. The atoms in the logic arithmetics is a proposition. Like, just like in the atom of integer arithmetics is an integer. And propositions are just statements that are either true or false. So for example, here's a statement that is true, 2 plus 3 is 5. And here's a statement that is false, 3 plus 4 is 6. 4 is a prime number. That's a false statement, right? 4 is divisible by 2. It's not a prime. It is raining today. I have this on the slide for several quarters now. And in Southern California, the statement happens to be false every time. But it will rain tomorrow, and unknown. Right, so it's clear. It's not so clear how to assign false or true to this. Of course, post factum you can assign truth or false to it. Chocolate ice cream is the best. It's a matter of opinion. Basically, proposition is anything that it's clear whether it's true or false. And there's many things said in English or any other human language, right, for which you cannot do this. Like a question has no truth assignment. A wish or a command, have a nice day, or some sort of exclamation, of which I'm sure you can give many examples, not true or false, right? Hold on a second.
Wait, real quick, the PowerPoint you uploaded is different to the one you're showing right now.
Okay, well, so you know what? I think that the only way I can fix it is after the lecture. And how different is it? Completely different?
On this slide, it's missing disclaimers in proposition
Okay.
slide.
Yeah, so it's still like an old version. Yes, you know what? But I think it's better if I upload it afterwards and you just go with the flow of the presentation here. But thanks for pointing it out. And sorry about that. All right. Now, of course, this idea that everything we say can be assigned an unambiguous truth or false value basically ignores all things about the human language, right? Which is that it carries all sort of nuance, emotion, humor, irony, sarcasm. It can be self-referential, and much more, right? So poetry is this type of, basically language can be sculpted. Or if you think of prayer, of incantation, right, where basically words have like almost magical property. Some people say that was, and maybe maintains to be the most important function of language. Mapping language onto logic is, that was a dream of some mathematicians and some philosophers, but it's clearly a pipe dream. And effects of language are hard to point down, the relation between it and logic, and not only that, like human mind, rationality, politics. There's many more where basically it's subject to endless investigations and debate in all sorts of areas, but and fascinating and very productive. There's a famous linguist from Berkeley. It's a flagship example. He had a book about quirky things about the language. It's called Women, Fire, and Dangerous Things. Enough said. And it's about basically the way we speak, that we carry all sorts of meanings, prejudices, preconceptions that are expressed in unclear at exactly what point, right? But yet they carry in the way we speak. So it's worth analyzing. Well, and in computer science, right? So basically right now we're at the moment when the power of AI, machine learning, can understand text and speech. It is not perfect understanding. Can it be? And likewise, generation of logical text and speech, right? So both recognition and generation are a few decades ago, nobody, I think, believed that we would be at the point we are right now. And so by that, who knows what the future advancements will bring. All right, so back to logic. So we denote logical propositions with propositional, what we call propositional variables, right? So this is like a variable in arithmetics, but its only assignments are true or false. And by convention, different branches of mathematics have different conventions, right? Like, so we denote angles with alpha, beta, gamma. We denote integers, x, y, z, or ABC, right? In logic, the typical convention is to use stuff like P, Q, R, S, as you know, a variable, anything, like when you program, right? You can set your variable in a program to be I, X, N, but it could be mama or daddy or, whatever you want, right? It's just that when you name your variables in a weird way, you will find that your colleagues have a difficult time parsing what you wrote. Same here. The values of these variables are truth and false, and equivalently, they can be represented as 1 and 0. So 1 for true, 0 for false. And purists would say that, no, you should only use P and F, and when you use 1 and 0, it's really not like. But truth is, we use both, and you are welcome to use both, and I will use both interchangeably. And I forget right now actually what the textbook does, but it sort of doesn't matter. Like you can do either one. I'm responding to a chat message that says, where are the slides? The most recent slide, I will post them after the lecture. All right. Conjunction. So, okay, first logical operation, conjunction. Conjunction is denoted with this funny symbol like an inverted V, right? And it's read as and. And P and Q is a statement. It's also a proposition. It's a compound proposition. It's formed from other propositions. The atomic proposition are P and Q. And P and Q is a compound proposition, which you can also think of it as a function of propositions P and Q. And this output of this function is true, so 1, in one and only case, if both P is true and Q is true. In every other case, it's false. So this compound proposition, the conjunction of P and Q is false. Now we can represent this in a truth table. So we can represent what this operation of conjuncting propositions, what it does logically as a truth table. Now, what is a truth table? Okay, so if a compound proposition includes however many variables, in this case just 2, P and Q, we write a truth table for all possible values of P, all possible values of Q, and as a function of these, we will, of whatever values they attain, we'll have the value of this compound proposition. Now, why did I put 4 rows, right? Well, because the truth table must show the value of the compound proposition for every case of the atomic propositions that this compound proposition involves, right? So in this case, I have 2 atomic propositions. Each of them have only 2 possibilities. But how many possibilities are there for the way that this pair looks, right? Like, so it's 2 for P, 2 for Q, and each possibility should be accounted for. So it's 2 here, and you multiply, right, to account for every pair. And by convention, when we make the first variable range slowly, whereas the next variable ranges faster. And if there were more of them, then the last one will have 0, 1, 0, 1. The first one would have these long waves, right? And this is completely by convention. You could permute this stuff if you wanted to, except that you will not be able to make any sense out of it. And for sure, nobody who reads this truth table will be able to make any sense out of it, right? So there is a value in this convention, which is that if you don't follow it, it's unreadable. So now, what is the truth table here? It's this. The rule for conjunction was that it was true in only one case, that both atomic propositions were true. That's expressed by the last row. If both atomic propositions are true, then so is their conjunction. In every other case, whenever one, at least one, here both of the atomic propositions are false, then so is the conjunction. And this agrees with the way we speak, right? When I say that, sorry, I forgot if I have an example or not. But if I say, you know, I will upload these slides, and I will also upload the video of the lecture. If I do one of these, then but not the other, then everybody will rightfully say I lied. You know, when I said that I will do both, it's obvious, right? And hence the conjunction is false whenever at least one of the stuff is okay. Somebody says in a chat that a different class had a different convention, which is exactly the opposite from the one I'm doing. Okay, interesting point. Don't know what to do about it, because everything I say is using this convention, and that's my sense that this is the convention people use. Okay, we have to take it, I think, offline, and you can, maybe I'm wrong. All right, so here is the disjunction, and disjunction is an or. It's denoted with a symbol v and a little v, and the compound proposition that says p or q, because that's how it's read, p or q. Or you can read it in a sophisticated way as disjunction of p and q. P or q is true whenever either of them is true or both. So in other words, the only case where the conjunction of p and q, where p or q is false, is when both both the atoms are false. So here is the truth table. Again, we write with the same convention that I'm going to stick for, you know, at least for now. Oh, you know what? Now I can see, yes, you are totally right. So somebody said that these iBooks have a different convention. Sure, yes. And you know what? So sorry. So yes, if you want to, you can range one of them. You know, you can switch the way they range. What is unreadable is if you permuted these rows. If you put this row here and this row here, and did all sort of permutations, right? Then nobody will make sense. If you just cycle using a different convention, that's okay. And in particular, yes, and we will be able to read it, and you are welcome to use either convention. All right. So here is this rule reflected in a truth table. The only time the disjunction is false is in the case where both of these were false. In every other case, it's true. And, you know, again, if I say that I will either put the slide up on the website or upload it to YouTube, again, that's true whenever I do. And it's also true if I do both, right? And oh, that reminds me, although this is not the best time to say so, is that some faculty pointed out, and there was some confusing, maybe I should say, instructions from the school as to legal aspects of placing videos on YouTube, since they contain possibly voices and maybe video recordings of students. So I should proceed, you know, at the beginning, I should always say, you know, you should be aware of this, although as of now, your faces are not really showing in these videos. But when we get to the question of answer, as hopefully we will, maybe your voices will certainly come in, and your faces might come in. And if you don't want yourself to be recorded, then switch off video perhaps when you ask a question. All right. So back to the conjunction. So note, that this is a kind of a controversial role. Not everybody, when I say I will do P or I will do Q, not everybody understands that this remains true if I do both. So this is actually a difference between what we call inclusive and an exclusive OR. Inclusive OR is the one I just explained. It's true if either propositions is true or both as well. And so, for example, if you say, this patient should not take the medication if she has a history of migraines, or she has diabetes. So it's obvious that if she has both, you also do not want to give her this medication. Right? We understand that. On the other hand, if I say, I will drive to work or ride my bike to work today, right? Then it's also obvious that I will not do both. I cannot do both, right? So there are all sorts of things in nuance. There is a background noise, so hold on a second. Oh, sorry about that. So of course we understand this in a human speech, right? But logically these are different operations, and there is an exclusive OR. It's a famous operation that's called XOR, and it's used all over the place in computer science, right? But in Boolean logic, the OR operation that I just introduced is always the inclusive one, right? It just stands for the inclusive one. And if you want to express the exclusive OR, you have to do so explicitly. And for this, you can use this in order to, as you will see in a second, but there is a special purpose operation. It's called XOR. And that's where the logic and casual English already start possibly diverging, right? Because as you just see in here, in casual English, OR very often effectively stands for exclusive OR. All right. Next operation, the complement. Complement is denoted with this symbol, like this, the negation symbol. And unlike the other two operations, it is an operation that has only one operand. So you negate one thing, whereas you conjunct and disjunct two. So the truth table of the complement operation is also smaller, because there is only one atomic expression, atomic proposition involved in it, right? Which has only two possible values, and the truth value of the result is just a flip. So if I say not P, then if P was false, not P is true, and if P was true, then not P is false. Right, so that's called a unary operator because it takes only one operand and it has only two possibilities. Okay. Well, we can already use the operations we introduced to build larger expressions. So let's look at this following expression. It is, I'm going to call it C for conjunction, and I will define C as a result of the following operations. Now, the way I explained conjunction is that you actually not sure how to read this, because a conjunction was supposed to be an operator that just took two operands. So how shall I read even this expression? So let's just think n is 3. So I'm ending my expression here. Should this operand be applied to P and 2 first and P2 and P3 first, and the result should be conjuncted with P1? Or should I apply this first and conjunct the operation with P3? So, but I can do this for this long step. So, I could read it either, okay, apply them in this order. First these, so like that, the result, end it with P3, the result, end with P4, and so forth. But maybe go from the other direction. Like here, you first do the last two and you take their end, then you perform end on the result, and so you go. So whatever this result is, you end it with P3 and so forth. In fact, you can apply this pairwise conjunctions because this is how we define the operation as a pairwise operation in any order you want. You can do these two and these two first, and then these two, and then take the result of this and the result of that and conjunct it. Now, why this order doesn't make a difference? Okay, because of a following simple fact. This whole conjunction is true only if all of these PIs are true, right? The moment one of them is false, then the whole thing becomes false. And why is that? So, okay, so look, you can apply, so let's have a parsing of it that is in any order, but let's just, okay, think of these two possible orders of evaluations, right? And note that whichever of these orders you take, then how do you evaluate? You do a conjunction of this, then the result is a conjunction again. And now what happens? You're starting from some values. The moment you encounter in this chain of evaluations any PI that is false, then the result of the operation becomes false, right? Because check the truth table for conjunction. Right, here it is. So the moment any of the variants, so this is PI and this is PJ in this example, right? The moment any of them is a 0, the result is a 0. So if you take this result and you conjunct it with whatever, you're guaranteed that whatever that is, you continue be getting zeros. The only way to get to 1 is on your atoms are all ones. Okay, so let's go back to this, right? So the first PI you encounter that is a 0, it makes the result 0, and then the result continues to be 0 no matter how. And basically this point is independent of the order. So that's why you might just as well skip the brackets, right? And the same is true for disjunction. Okay, but for disjunction, the reason why this is so is slightly different, although logic is very similar. Namely, if you take this big disjunction expression and really define it to, you fix the order of evaluations. Okay, let's say like this, or like this, or you can actually apply any order you want. Then any order you pick, the way you evaluate it is that the moment you encounter any PI that is true, the result of this disjunction is going to be true. And therefore, whenever you disjunct the output with whatever, this is going to continue being true, because that's how disjunction works. If I say A or B, the minute one of them is true, then this whole thing becomes true, right? So if you think of this as a circuit evaluation, there was a 1 at one compound, and then every wire in the circuit becomes a 1 as you evaluate. So the output is 1. So again, you might just as well skip the brackets. And by the way, this is what we do in human speech, right? So I can say, if I have five things that I'm going to do, I can say, I will upload the slides, I will post the lectures, I will respond to Piata, I will, talk to the TAs. And I didn't have to say, put brackets in between these operations, which were all ends, right? So it was more the conjunction. It was an example of a statement of this form. And if I, okay. All right, so, but with conjunctions, disjunctions, and negation, you can, basically this case of one big conjunction of stuff and one big disjunction of stuff is really the only where the order of operands does not matter. Anything else you write, the order of operands is going to matter. And so take this minimal expression of this type, right, where we have all our operands. And well, it's clear here the not has to be applied to R. You know, there is no other possibilities. If this not was right at the beginning, I would start having questions about it. But about the or and an and, there is a question. Should I first conjunct Q and not R and then disjunct the rest with P? Or should I first evaluate disjunction of P and Q and then evaluate the result ended with not R? If you look at the truth table of these things, you will see that they differ. They're not equivalent. So the order of these evaluations matter, and we have a fixed in logic order of precedence. So whenever you see a complement, you have to apply it first. And then when you have conjunctions and disjunctions, conjunctions take a precedence. So this expression should be evaluated, take the conjunction first, look at the result of this, and then disjunct it with P. And it's not ambiguous. On the other hand, it's still good to use parentheses because in practice, humans tend not to remember. And even if they try to remember, it is very hard for them to parse these expressions. So there is some order of that is considered obvious, like complement, where so if you really wanted to put brackets on everything, then the problem is that expressions are hard to read because there's brackets all over the place. If you don't put brackets at all, they're hard to read also. It's a matter of convention and practice, whether, you know, I cannot tell you something else because that's really the case. So you have to, you know, we'll bear with you if you overuse brackets, and we'll try to bear with you if you underuse brackets, and hopefully you will get the sense of what a good convention is. So typically we ignore brackets when we mean complement, and when we have a chain of dis-ors or a chain of ands, just like in the two slides before, right? But here, I would not rely on human remembering that a conjunction is first. So if I wanted to write this, I would put brackets in here, right? And that's a good practice. Okay, so let's look at what happens if we have the compound propositions and how do you evaluate them, right? So let's do this one that we had on the board just now. And so let's try to evaluate this, right? So how do I evaluate? So, okay, so I mean, for my human readability, I would replace these and or signs with the, you know, with this. So it's okay. You don't have to do that, but like for now, for the purpose of presentation, I would do that. Well, now I can substitute, right? Because I know that P is true, Q is false, R is true. So I'm just sticking up truth and false for. Oh, and I have made a mistake. Okay. Oh no. Okay. Okay, good. Screen sharing stopped. Hold on a second. Okay, back to programming. Sorry, there was a typo. No, sorry about it. From the current slide. Okay, and now screen sharing. Boom. Okay, so I think we are back. Sorry about the typo. All right. Okay, so let's see if that fixed it. So this was my rewrite. Now R is false. So P is true. So I replaced it with this. Q is false. Okay, R is false. All right. So now I have the fully instantiated expression, and now I can apply my Boolean formulas, right? Because so what precedence can I take? Well, the first guy to go is the negation, right? Okay, so I applied the negation to things, right? So negation of tree is, of course, false, and negation of false is T. So I rewrite it like that. Now I can apply the conjunction, and I know that a statement that says false and true is false, right? Because one of the propositions was false, so the conjunction is false. And a disjunction, well, that's the only case of disjunction being false. Both of these guys are false. So if I say either that or that, it's still false because both of them were false. If I go to the other one, let's do this again. So, okay, so I just, for my readability, I put it or, so it's easier to read. So it's a negation of P or Q or not R. Okay, so I instantiate them now. So it's negation of something that is true or false or not false. Well, I can evaluate this thing. So it becomes true or false or true. And as I said, disjunction is true whenever one of them is true, right? So it does not matter what order you evaluate this. The minute one of them is true, then the whole disjunction is true. So it's like this. And now you can apply the negation, so it's false. Now, you can, this is not, this is not an order that you have to evaluate it with, right? You can do shortcuts. For example, look, in the first line, it was not P or something. Perhaps I don't even have to look at that something very closely. Let's focus on not P. So I might observe that P is true, and therefore not P is false. And I might also observe that the logic of the disjunction operation is such that if I say it's false or something, then that's really equivalent to just saying something, right? Whatever that thing was, if I said one of these things is true, the first is obviously false, and the other is something, then what I said is that I claim that that something is true, right? This is, if you look at the disjunction truth table, it will jump at you that if you fix one variable to false, then disjunction is an identity on the other variable. P false or P is P. Just like truth and P is equivalent to P. So at that point, you could have rewritten this line as immediately Q and not R, right? Because this whatever expression here is really stands for, in this case, P and not R, right? So you can do anything you want really here, right? I mean, as long as it's true. Okay. Well, so here was an evaluation for a particular case of instantiations of these variables, right? I go and evaluate these propositions using the definitions of all these operands. But I can also basically show to myself what this expression is equivalent to for all possibilities of P, Q, and R. And that's a truth table of an expression, right? So here is a truth table for this proposition. Because this proposition now involves three atomic operands, three atomic propositions, P, Q, and R, my columns there will be three columns. And the reason that there will be 8 rows is that each of them has 2 possibilities. So the total number of possibilities of a triple is 2 for these, 2 for these, 2 for these, if you multiply. That's how many triples there are, and somebody wrote it nicely on the chat right here, right? All these. Indeed, that's how I will write them, and you're welcome to have the other conventions that somebody mentioned, the student mentioned, the textbook uses. All right. So these are all my choices, right? There are the only 8 possibilities of what these P, Q, and R variables what values they can attain. And in order to evaluate this expression, right, I would write a truth table that involves the atoms in those expressions. So the atom in this disjunction is not P, and I have a column from not P, and the other atomic in this disjunction is a conjunction of Q and not R. So I will have a column for that. Now, what do I need to evaluate this? Well, I have to know what a Q is, but I already have a column for that. I also need to know what the non-R is. Let's just write a column for that. Okay, and now populate this table. So not P is very easy. I just flip the values of P. So they look like that, right? Because not 0 is all became not 1, became 1, and not 1 became zeros. Not R, well, I have to identify the column and just flip the values of R. So they look like that, right? The 1 is a flip of 0, 0 is a flip of 1, etc. And now I basically do it so that I can evaluate these next expressions without making mistakes, right? So look at evaluating the conjunction Q and not R. I know for every row, I know what a Q value is in that row and what a not R value is, and then I just conjunction. So here, conjunction of Q and not R is a conjunction of 0 and 1, so that's a 0. In fact, conjunction, I can evaluate it like this. Whenever one of these atoms is 0, then it must be 0. So here, Q was 0. Here, both of them were 0. Here, both of them were 1. And here, not R was 0. If you might observe that you don't have to really evaluate it, you can copy, because the lower half is the same as the upper half as far as Q and R are concerned. The only difference between upper and lower half is a status of P. If you have expressions that ignore P, like this one, then this stuff is just a copy of this stuff. Okay, and now let's look at this expression, right? So it's a disjunction of not P, so it's going to be disjunction of these values with these values. And what I know about disjunction, it's true whenever one of them is true. So I basically can, whenever I see one true, so here I see it's this one, here I see it's this one, here it's both, here I see it's this one. Now not P is all 0, so it's a copy of this, right? Look, this stuff is copy of this. Why? Because here not P is 0, and as I said, you can look at the truth table of an and if one of the operands is false, and with false is equivalent to the other guy, and therefore this column is a copy of this one. And yeah, and another thing about an OR is that whenever one of them is 1, then the result is 1. Since here they were all, this guy was 1, I can just write this, right? So there are shortcuts. Understanding how these things work will be able to, you can write stuff faster. But then again, you have to understand how this works by just doing this. And, the more you do it, the more intuition and noticing that there are shortcuts in this that you will be able to observe. So the more you do it, the faster and better you become at this, right? Okay. In general, there is a notion of logical equivalence between expressions. So two expressions, like for example, this one, not P and Q. So this one says it is not true that both P and Q hold. This one says it is true either of the following things is true. It's either that the P is false or Q is false. That's what this thing really says. And one can observe that this and that say the same thing. Well, you can verify it using truth tables. So because both expressions involve only P and Q, the truth table will have two columns for two variables, and so it will have 4, right? Because 2 times 2 is 4 rows. And now let's evaluate them. And I, in order to write like a nice truth table, I should have a column for P and Q for this expression. And then this expression should have a separate column, and it will be a flip. But I'm going to shortcut this. And I'm just going to evaluate P conjunction in my mind and then flip in my mind, right? Well, we'll all do this together, right? So P and Q is false in all these cases, right? Because one of P or Q is false in all these cases. So in the first 3 rows, P or Q is false, and therefore its flip is true, right? Its negation is true because the conjunction of P and Q was false in all these places, right? That's the truth table of a conjunction. And the only time a conjunction is true is this row. So the conjunction is true, and therefore its flip, its negation, is false. Okay, let's evaluate this in this kind of shortcut way. Okay, so this is a disjunction between a flip of P and a flip of Q, right? So it's a disjunction of, in this case, true and true, because I'm flipping P and Q. So the disjunction is true. Here it's a flip of, I'm disjuncting, I'm saying either not this or not that, where not this is 1, so that's enough for me to say that the disjunction is 1. Let's move to the third row. It's a disjunction of not this and not that, where not this is a 1. That's enough to write a 1 here. And the only case I'm going to get a 0 is here, because disjunction of not true, that's a false, and not true, that's a false. So I took either false or false, and therefore I got a false. All right, well, you can use a good. It is exactly an AND gate, so it's a not an AND. So in Boolean logic, this operation has a name. It's called NAND for not an AND. Okay. So you can write the full truth table if you want to, or you can do shortcuts in it. Of course, doing shortcuts might lead you to a mistake, but I can swear to you that there was no mistake in here. So again, why is this? So you seeing this truth table, these expressions are equivalent. Why is that? Because for any assignment of P and Q values, this expression and this expression have the same values. So for all P and Q possibilities, this thing and this thing will evaluate identically. In other words, looking at this as truth tables is a very simple thing. Two expressions are equivalent if they have the same, if their columns in a truth table are identical. Yeah. Okay. But you can also quickly test this equivalence. You might not be able to find out this equivalence very easily, but on the other hand, if you think of what these Boolean expressions mean, you might, right? So the following two things are true. the left-hand side, namely this expression, the NAND gate, is false if and only if this thing inside is true. But this thing inside is true if and only if both P and Q are true. So therefore, left-hand side is false if and only if both of these guys are true. Now let's look at the right-hand side expression. And here you have a disjunction. So the easy case is the most discriminating case, is to look at when does disjunction produce false, because that's the least frequent, right? Like you have to, that's the one that, the case that constrains the atoms the most. The only way disjunction can produce false if both of these are false. But if the negation of P is false, then that's equivalent to P being true, and the negation of Q being false is an equivalent to Q being true. So again, you have these two laws, and therefore these two things are equivalent, right? Because basically what they both say is that it is not the case that P and Q are both true. And this is actually called De Morgan's law. Okay, it is this rewrite. You can think of this as a rewrite procedure. Whenever you see this expression, you can replace it with that one if that's for some reason convenient, or vice versa. If you see this expression, you can express this with that one if that is convenient. Why? What does it mean convenient? Well, whatever expression this is part of, because I'm a compound expression, the resulting expression is now easier to evaluate. Like, for example, it becomes one big chain of disjunctions if you replace a nasty looking atomic thing in a bunch of disjunctions with, and you say, oh, well, oh, wait a second, this is all a hidden conjunction too, disjunction, sorry, too. So you rewrite it like this, and the result is now a bunch of disjunctions, and you can, yeah? Here is some application. So look, this is also what humans say. So here is some admission rule. For example, the applicant must be 18 years old, and also the applicant must have a valid driver's license. So there's two. So you express an admission that you have to have. So you could express this admission by saying, I will not allow driving, or I will not allow somebody into a bar if it is not true that both of these hold. So that it's not true that they are 18 years old and that they have a driving license. So when you say that, you see that the conjunction of these two statements must not hold. So the only way that is true is that if either the first part failed or the second part failed, either one might fail, but you're saying that one of them did. So another way to say it is to explicitly say, okay, one of these conditions is false. And how do you say it? With a disjunction. Because that's what a disjunction is, right? So that's this statement. Okay, let's look at the other De Morgan's law, that a negation of a disjunction is the same as conjunction of negations. How can you quickly test that? If you look at the opposite case, look at this conjunction. The easy way to discriminate conjunction is to say when it is true. The only case it is true is where both atoms are true. In this case, not P must be true and not Q must be true. So therefore, the right-hand side is true only if and only if both atoms are false, right? Because that's, if P is false, then this thing becomes true in the only case. And the only case where this thing becomes true is that Q is false. Let's look at the left-hand side. This is true exactly at the moment where the inside of this negation is false. And when does the conjunction become false? In only one case, that both of these atoms were false. So you have this row. And now you convince yourself that both of these expressions are equivalent to stating that both P and Q must be false, right? So this also has a name, right? It's a NOR. It's not a NOR. So in Boolean logic, that will be the name of this compound operation. Take an OR and flip. And look, that's the example with the patient who has a history of migraines. I can administer the drug if it is not true that somebody satisfies either condition, and therefore, in order to administer the drug, I have to check that both the first condition is false and the second condition is false, right? Because the moment one of these conditions is true, then this compound expression becomes false. All right. Another important operation, implication, right? So it's denoted with a symbol, an arrow, sometimes a double arrow. And the way we read it is that P implies Q. But also you can read it as if P, then Q. So whenever P happens, then Q must happen. And in fact, there is many more ways to render it. And some of them might not strike you at first as here is some of them as well, as equivalent to basically saying that P implies Q. And there are some good exercises in the book and on the homework as well. By the way, I want to attune people to the fact that the textbook has many exercises, and I leave solutions open to many of them, so you can test yourself. You can see, try to solve it, and then compare your solution with the one you click and open. I don't believe that opening solutions immediately really teaches you anything. You are welcome to do that, but it's a waste of time, I think. Okay. So what's the truth table of the implication? And it's actually, it starts getting kind of quirky. So this is the truth table of the implication. And well, it's easiest to see in the lowest row. So if I say that if P, then Q, so whenever P happens, then Q must necessarily happen. Well, if P happened and Q happened, then I say, well, if this implication held, at least it wasn't violated. In here, this row, it was clearly violated. P in this world is true, and Q is not. So whoever says that Q must be a necessary implication, a necessary conclusion of P, was not saying the truth. Because here's the world where P happened, but Q didn't. Okay, P is true and Q is not. So whoever says that if P then Q, well, P holds. So how come Q doesn't? Well, because the implication was false. These things are a little strange. So what happens if P is false? If somebody says that P implies Q, but P is actually false, it's sort of like you cannot test whether that's true or not. Because, you know, when somebody says that whenever P happens, then Q must happen necessarily true, but P didn't happen. And in logic, we just basically declare that the implication is true. We declare the implication to be true in the sense that the implication was not violated. That's really kind of like a meaning. if you use logic for something, then these things will have meaning. Like this is a little bit arbitrary, but that's the expansive notion that it is, if it's not explicitly violated, then we declare it to be true, and it's consistent in a system. It has some bearing to the real world way we speak. So, okay, so if someone says, if you mow my lawn, I will pay you $20. So the statement, you mow my lawn, M, and the statement, I pay you $20, these are two different prepositions, right? They can be either true, you mow my lawn, or false, you don't. And P, I pay you or I don't pay you, right? So these are propositions. They're either true or false. And now we can look at the table of what, this is really a truth table, right? And but in a different visual representation. M, not M, P, not P, right? And what is the truth of the implication? If I say, if you mow my lawn and I will pay you, well, both of these things happen. So we declare it to be true. But if you don't mow my lawn and I still pay you, was this implication true? Well, we would kind of never know. But at least nothing was violated about it. Now, if you mow and I don't pay you, I clearly have violated what I have said. Okay, so what I said was false. And here it's also true. A good example is the Fiddler on the Roof and If I Were a Rich Man song. So for those who know this song, if I were a rich man, I would do all sorts of stuff. I would give my daughter this wonderful wedding. I would, build a beautiful house and so forth. Forgot what the song says exactly. The point is, forgot the name of the character who sings this. He's not a rich man, and therefore, all his pronouncements of what would happen if he were a rich man still can be true, right? Even though none of the conclusions are true either. And basically, this is in this case, right? If you are not a rich man, all sorts of things can happen, and we don't care if you say what would happen if you were a rich man. Whatever is the case, it doesn't violate the implication. Here is an equivalence that you might find useful. A conditional P implies Q can be thought of as a disjunction. Not P, either not P. So either the hypothesis is wrong, or conclusion did happen, does hold. So if you look at the truth tables, this is just a fact that the only case where the implication P implies Q is violated is when P was true and Q was not. And that's also this only case where this disjunction is false. It's when P was true and Q was false. That's when this thing becomes false and this thing is false, and that's the only case where this disjunction fails. Now, so you can quickly see that these are equivalent, but is this so in the human? So well, look at an example. I say I have a proposition C and D. Proposition C is that a certain integer is a composite, meaning what's a composite in integers? That it can be represented as a product of two other integers which are non-trivial, like it's not 1 times the original integer or -1 times the minus original integer. These are the trivial ones, right? But there are some other factors, right? So like 10 is a composite because it's the product of 2 and 5. So that's a proposition that some number is a composite. And by the way, whether a number is composite for a very large numbers or not is actually not trivial to test this. And here is a proposition D that the same integer has non-trivial divisors. And I make a statement that proposition C implies D. So if a number is composite, then it has non-trivial divisors. Now I can express the same thing differently, like so. It is either the case that a number is not composite, in other words, it's a prime, or it has non-trivial divisors. And you can see that both of these statements are true, and it's also true that actually they are equivalent. Okay. So the only way to violate this would be if there was a number which was composite but had no divisors, non-trivial divisors. There is no such number. The only way to violate this, if there was a number such that it was not composite, or it doesn't have non-trivial divisors, again, there is no such number. All right. Another rewrite rule, counterpositive. So counterpositive can be explained as an equivalence between the following two expressions. P implies Q, and not Q implies not P. So here is an example, and I say, if Susie studies, then she passes the class. Now, if I say, if Susie doesn't pass, then she didn't study. That's the same thing. So the first statement says that if it is the case that she studies, then it must necessarily follow that she passes. That's what the first statement says. So how about stating it the opposite way? So if you are telling me that if somebody studies, then they necessarily must pass. So let's take it from the back. The only way somebody might not pass, if somebody does not pass, then it must be that this hypothesis is violated. Because if it was true, then it couldn't have been the case that somebody does not pass. So if they do not pass, then it must be that the P was not true, so they didn't study. So I can express the same thing using counterpositive. If the conclusion was false, then it must follow that the premise was false as well. Yeah, and the two things, if you write the truth table, you will see that they are equivalent. Okay. This is, by the way, a common proof technique in cryptography. The way to argue that if some cryptographic procedure is secure, then a construction that uses this procedure is secure. Let's say if I have a secure block cipher and I want to make from it a secure hash. And my construction, I can prove that if the block cipher is secure, then it must necessarily follow that this constructed hash is secure. Well, the way I can prove it is the following. If the hash is insecure, so there is an attack on the hash, then I will argue, and you can't know unless you study cryptography a little bit how to do that, that the attack must effectively attack the block cipher. And therefore, if I believe that the block cipher is secure, then I must believe that the hash function is secure. The two things are equivalent. And in fact, that's how we prove cryptographic construction secure. Because how can we prove that if there is no attacks on encryption, then there must be no attacks against the hash? Well, we cannot really look at all attacks. But hey, if we say there is an attack against hash, so let's posit that there is some algorithm that attacks the hash, and let's use that algorithm to attack the encryption. And what we ended up proving is this implication. Well, all right. So the counterpositive, and if you look at the truth table of these expressions, you will see that they're equivalent because this row is the only one that they are false. Why is it? Well, here this is by definition, and here because the only way to falsify it is when this thing is true and this thing is false, right? That's the only case the implication is false. If you start with a correct promise, but you end up with a false conclusion, so not Q is true, not P is false. Not Q is true means Q is false. Not P is true is false means P is true. So that's the only row that is going to falsify this expression as well. Okay. 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 Well, funny thing is that you can derive this equivalence using stuff we know, because if P implies Q is equivalent to either the hypothesis is wrong or the conclusion must be true. And if you look at this counterpositive, well, let's use the same rule. Either the premise is wrong, that's negation of the premise, which was in this case not Q, or the conclusion is true, the conclusion is not P, so it's this expression. That's application of the same rule, but now applied to not Q and not P. So that's what I stuck in here. And if I rewrite this, well, obviously negation of Q is Q and not P stays not P. And then we flip the sides because the order does not matter in disjunction. And so obviously this and this is equivalent, right? So that's another way to see it. We are nearing the end. So, you know, the best I guess I can do is to just flip through this. Perhaps there is not much point in this. You can do it at home on your own. So I should open up to questions. Please speak up if you have any. I assume everybody can unmute themselves. So somebody asks, when are the reading assignments due? You read on your own pace. I recommend that you read in synchrony with lectures and discussions and homeworks and tests for obvious reasons. But in this class, I'm not going to monitor the timing with which you do the readings. Press space to unmute. Oh.
Unmute. That's why I think you said.
I didn't do anything, and somebody spoke. So I think you do have a control over your mutes.
Yeah, we do. So, quick question about do we need to derive equations, or this is just understanding them and how to apply them?
Well, you see the homework for what kind of stuff I expect you to know how to do.
Okay.
There's all sort of types of problems you can ask in this. And in the lecture, I only reached I don't know, section 1.6 or something, and there is at least 4 more subsections for you to read. So I might what I might do is you know, if people enjoy me jabbering, I can record this remaining of this lecture and post it as well, and people can peruse it at their leisure. More questions? So long as those required PACAs are done by the end of the quarter, we will receive full credit. Yes, but I very much encourage you not to do this. I mean, like, if you say you can read everything at the end of the class, you will do terribly in the class. I pretty much guarantee to almost everybody, except if somebody is like knows this stuff perfectly, okay? But then, by I don't think there's so many of you like this. I mean, like even if you know logic well, if you took it before, you start doing the stuff, you will see that there is stuff you will learn. Should I read off questions that people ask, or maybe somebody wants to ask them in speech? Please go ahead.
Professor?
Yeah.
You mentioned that we covered up to 1.3 today, something like that, somewhere around there?
I don't know.
Okay, I'm just wondering because the syllabus said that, oh wait, no, never mind, I read it wrong. Never mind.
Yeah, it's basically the whole first chapter until 1.10 is this week. And so I will record another one with some remaining stuff, for some people might find it helpful.
What about the chapters 3 and chapters 4, the sections 1.1 to 6 and 3, and 1 and 3 to 4 in section 4?
So they are on the syllabus. I placed them for next week.
Oh, those are next week's reading?
Yes. So yes. So we try to do stuff in sync: lectures, discussions, reading, homework. This week is about logic. The syllabus. I have to stop sharing the screen, I guess, to look at the syllabus. But the syllabus, I'm pretty sure, says that.
Yeah, it says week 2 is chapter 3 and 4.
Yeah, that's right.
This isn't necessarily pertaining to today's lecture, but is there any way that you can post the Zoom links to the class website or pin them on a message on Piazza? I ended up joining the lecture late because I wasn't able to find the link.
Wait. A link to what?
To Zoom.
To Zoom. Oh yeah, with the right. Okay. Yes. That good point. Yes, it's in the Piazza discussions, but
yeah, it's
but
not
let's just
easily
put it.
found.
Yeah, exactly. Good. Yes, I'll put it on the good point.
Thank you.
Mm-hmm.
So homework is graded based off correctness, right?
Oh yeah, I talked about this. We have no powers to enough enough human power to verify everything. There's just too much. So we will verify occasional problems and verify like, oh, looks like you've done it all. This is kind of unfair, but I see no other way around it. Homework is not worth all that much. So, these are small. I mean, the chances that, we verify problems that you happen not to do, I mean, basically you are supposed to do all of it and you're supposed to do it well. And yes, if you happen to get like some stuff right and some wrong, and we just verify the ones that you happen to get wrong, you get unlucky. I'm not sure how to go around it because I think that an effort of TAs on understanding some questions in giving you feedback on them is more valuable than on trying to plow through all of this. But that will be different on tests, where obviously we'll verify everything in great detail. So you are expected to learn from solutions and sort of be adult about it. Like you are expected to understand the solutions and how your solution differs from the one we give. And if it does, then understand why that is. And if you don't, then bring it up. Then post it on Piazza, bring it to the discussion, why the solution doesn't work. Or if you have an alternative solution and you're not quite sure why, then sure. But there will be alternative solutions. There will be solutions that you have, and they will all lead to the same. If they're all correct, then they lead to the same answer. But that's the numbers are stuck up against it. I mean, that's why grading is done in this fashion, that homeworks in the end are a small percentage, and the understanding is that you will basically practice the stuff, and the way you test it on it is in tests.
Another question is about is there, how when you're reading those iBooks, you have those problems to do? Those problems, like, do you want us to do that for homework as well? Is that homework? Because that's in the homework as well too, right?
Some of them, the homework says which problem is on the homework.
Yeah.
So some of them are from the textbook, some of them are not. And what I'm saying is that the textbook includes many more exercises, and it has this kind of convention that the teacher can either open a solution, so everybody who's taking the class and subscribes can see what the solution is, or the teacher can close. So if I assign a problem, of course I close it, and we try to synchronize with the other teacher, so that I don't open the ones she assigns and she doesn't open the one I assign. And you're very much encouraged to look. There is a very similar problem in the homework, just has different cases. Try to solve it and try to see what the solution is and learn from that. There is a I don't expect you to do all of them, because it's just too much.
Okay.
Hi, Professor.
Hi.
Are we allowed to discuss homework problems before the due date on Piazza?
Yes, you of course, yes, you are allowed. You just should not post the solution. Okay, because you don't spoil
we can talk
it.
about the idea, right?
Yes, well, it has to be a judgment of, like, is the idea completely revealed or what? I mean, definitely if you say, okay, I don't understand this because, then somebody can say, oh, look, this is how, and other students can help you and we can help you. That's exactly what Piazza is for. Just don't solve it for other explicitly.
Thank you.
And you're
Hi,
able to
Professor.
collaborate with each other, but we want the groups that collaborate up to
Professor?
3, and you have to acknowledge collaboration in your solutions. Another question?
Yeah, hi, Professor.
Yes.
So from seeing the syllabus, I don't see all the sections of the Zybook being covered. I suppose all we need to do is the sections mentioned.
Yeah.
The syllabus, or
the syllabus right now has only 4 weeks, and there is a link at the beginning that says, if you want to see what's ahead, go to the previous quarter, and you will see what the rest of the class covers. It's just that I don't think there's a point like saying exactly what's going to be on week 6, because things might shift slightly depending on the speed with which things go and so forth.
right. Essentially, my question would be: do we have to do the entire Zybook from chapter 1 to 14, or just
No.
the sections indicated from the syllabus? That's all my question.
Section indicated in the syllabus. Yes, only the latter. And look for spring 18 syllabus to see roughly which chapters we cover, because we cover only select few chapters, like 5 or so.
So, Professor, so we don't necessarily need to finish the reading in chapter 1?
Yes, some sections, like section 11, 12, 13, is not required. There's enough stuff as we do. Okay, of course you are encouraged to read it. Of course you are encouraged to expand and to see. There are sort of great stuff, but it is not required.
Oh, so we all need to finish up from 1 to 10 in chapter 1?
Correct, because that's what syllabus says.
Okay, thank you.
Yes.
You're welcome. Any other questions?
Test. Hi, Professor.
Hi.
Do you have to do the participation activities and challenge activities part of the
Yes.
Zybooks? Okay.
Yes. In fact, I don't know what else, you know, just passive reading. I'm not sure whether I get like any report on that. I mean, reading really means doing these exercises. Yeah. So if you want to, you can don't read, just do exercises. But no. That's a joke. Any other questions?
I don't know if this is asked already, but are we allowed to work with like in pairs, like three for homework and stuff?
Yes. Yes, but acknowledge collaboration. Any collaboration should be written on your homework. I worked with boom, and up to 3 for fairness to others.
All right, so I just write the names of the people I'm working with?
Yes.
All right, thank you.
Exactly, thank you. Oh, when somebody asks a good question, when the question asks you, invoke general logic laws for proofs, do you have to spell out the laws? No, it sort of depends on the question. I think that none of the questions I say, well, it's a kind of a thing like, you know, if the law is obvious, you don't have to say it. You can just rewrite using it. If it's not, you should write. In general, you know, you don't have to write why negation of a negation is the same as the thing itself. You don't have to write that a conjunction of 3 things, you don't have to evaluate the order. But if you have a more complex change, we would appreciate it if you wrote why. It's also a good practice for yourself, right? Because otherwise you cannot, I mean, understand what happened. Any other questions? Okay, somebody asked homework graded on completion or correctness. Again, it is graded sort of haphazardly. It's graded by completeness, like, so it looks like you've done stuff that we asked, and then select exercises will be graded in detail. And you know, you can basically expect that the ones that are graded in detail are the more complex ones, because that's the ones where we can give you some useful feedback for. Is everything in the homework mandatory? Yes. Yes, yes. Homework does not say like you can do either this or that. No, homework lists stuff that we would like you to do. And okay, so there, and you know, there is a lot of material of the logic, and that's the you know, the unfortunate of this class, that like we start like sort of having to sort of get this logic base, but then jump from that to other things. Note that the first test in the class is in 3 weeks. So you really have the time to ground this more. But technically on this first homework, you have to give these answers by, you know, Tuesday, 5 p.m. I mean, not just technically, you have to. Any more questions? All right, guys and girls, take care of yourself, and I will post this, and I will post updated lecture notes, and also record a little more stuff on the remaining of the first chapter. All right, thank you so much. See you next time.